Right, so welcome to Math 319 Operations Research. This is lecture 9. And so what I want to do today is I want to continue with covering material related to solving linear programming problems while at the same time reviewing linear algebra. I know it's been a while since people have done linear algebra in some cases. It might have been done during the pandemic, which is another story in itself. And so what I want to do is I want to go over some of the key concepts of linear algebra and then talk about how can we use this to help us find solutions. And again, for many of these problems, it's trivial to write down an algorithm that will get you to the solution. Check all possibilities. And it may be very easy to come up with a way to label and work through all the possibilities. It may not be that difficult to enumerate them in terms of just explicitly listing them. Why don't we do that? Why don't we just enumerate all the possibilities and check and see which is best? Super inefficient is not even close. Extreme, I mean, whatever words you want to use would not be underselling it. The number of possibilities is 10 to a huge power. We've talked about every subatomic particle is a universe, and each one of those is a supercomputer. We can't even make a dent in the problems. So even though theoretically we could easily write down an algorithm, it's the same as trying to factor a number. How do you factor a number? Well, the simplest thing is just check and see all numbers less than or equal to your number. And then with a little bit of work, wait a minute, I only have to check numbers up to the square root. Because if I can write my number x as a times b, if a and b are both less than square root of x, so is the product. So I only have to check up to square root of my number to find possibilities. But this is extremely inefficient. It takes so long that it's not practical. And to date, there is no publicly known easy way to factor numbers. Nothing that's efficient. Amazingly, we do have fast ways to tell if a number is prime. So we can often tell if a number is prime without knowing whether or not this is its factorization. So here, what is the first concept? I want to review the concept of linearly independent, and of course, walking in sync with this is linearly dependent. So we have some vectors v1 through vk, and we'll assume that the vectors are non-zero, because if any of the vectors are zero, things are trivial. So we've got a bunch of non-zero vectors, and imagine a combination of them is equal to 0. So alpha 1 times the first all the way down to alpha k times the last equals 0. Then they're linearly independent if and only if all the alphas are 0. So of course, one direction is trivial. If all the alphas are 0, then clearly the linear combination is going to be 0. But if I want that linear combination to be 0 without the alphas all being 0, then that would mean that the vectors would be called linearly dependent. So imagine that you have a situation like this where this combination is 0 and not all the alphas are 0. What can you tell me if not all the alphas are 0?
All the vectors are unique, or they're not scalar multiplications.
Okay, so one is that they're not scalar multiplications of each other. Good. What else can we tell if I tell you that the alphas are not all 0? So as soon as I tell you all of the alphas aren't 0, what do you know? Well, we'll call the vectors linearly dependent. So how many alphas have to be non-zero? Is it possible that there's just one alpha that's not 0? Well, that doesn't, I could have 3 of them that are non-zero. But we know that there has to be at least 2 alphas that are non-zero. If only one alpha were non-zero, then one of the most important phrases in math is without loss of generality, log. So without loss of generality, if only one is non-zero, let it be alpha 1. And then you would get alpha 1 v1 equals 0, so v1 is 0. So if they're linearly dependent, you have to have at least 2 alphas non-zero. Without loss of generality, which 2 alphas should they be? 1 and 2. So without loss of generality, we're labeled. So if linearly dependent, without loss of generality, alpha 1, alpha 2, do not equal 0. So you can get V1 equals negative alpha 2 over alpha 1 V2 plus dot 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 plus, sorry, I guess these should all be minuses. Dot 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 minus alpha k over alpha 1 VK. So if the alphas are not all 0, at least 2 of them have to be non-zero. I can divide through by alpha 1, and I can now write V1 in terms of everything else. So I don't really need all these k vectors if they're linearly dependent to span the space. I can do it with k minus 1. And of course, if 3 of the alphas were non-zero, or 4 or 5, that's possible. I just know that there has to be at least 2, so at least something on the right-hand side is not 0. And then, of course, you could ask, what's the smallest number of vectors that I need to span a space? Or what's the largest number of vectors I could have that are linearly independent? So if you live in n-dimensional space, what's the largest number of vectors you can have that are linearly independent? N. And then in other spaces, it's not clear what is the basis. So for example, what if my space is 1x, x squared, x cubed, dot, 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 dot? I could give you a space of functions. And I could ask, if I give you the space of functions, I could look at all linear combinations of these. This might make you think of Taylor series. And then the question becomes, how do you handle a space with infinitely many components? It's no longer clear that every sum converges. So things become far more complicated as soon as you hit an infinite dimensional space. Out of curiosity, how many of you, when you did linear algebra, worked in an infinite dimensional space at some point, explicitly? All right, so for the most part, you did not do things in infinite dimensional spaces. Okay. In a finite dimensional space, there's never any difficulty of, does the sum converge? Yes, the sum converges. If you have 2 sums and you want to switch orders, not a problem. As soon as infinities enter the problem, it becomes much harder. Fortunately, for a lot of what we're doing, we are working in finite dimensional spaces. The finite may be astronomically large. It could be of size 10 to the 400, but it's still a finite number. And as long as things are finite, we have no real concerns. Okay, so you can have a lot of questions asking about are various things independent or dependent? If I give you 3 vectors in the plane, what must be true? They must be dependent. And without loss of generality, generically, if I give you 3 vectors, usually any 2 of them will form a basis. What's the only danger when 2 of them would not form a basis, when 2 of them would be dependent? They lie on a line. And if I give you 3 vectors in 3 space, odds are it forms a basis. The only problem is if the 3 vectors somehow span a plane and live in a plane. Basis means that you can write any vector in your space as a combination of elements of that set, like a linear combination. So a basis is spanning. Everything can be written as a combination. And a basis has the fewest elements necessary. So for instance, for a basis for the plane, I could use 1, 0, and 0, 1. I would not use 1, 0, 1, 1, and 0, 1. That gives me too many elements. You can, of course, write everything in terms of that. It spans, but it's redundant. It has more information than I need. Okay. All right. So the next thing is I just want to review, because again, different people teach linear algebra from slightly different perspectives. What does it actually mean to calculate AX? Well, one way of looking at it is I can view the matrix A as a collection of column vectors. So if A has, n columns, then my vector X has to have, n entries. And I can view AX as x1 times the first column plus x2 times the second, all the way up to xn times the last. So if AX equals B, this means B is in the column space of A. If I want to solve AX equals B, B must be a linear combination of the columns of A. If not, then there's no way I can solve AX equals B. If you want to solve AX equals B, what would be wonderful about the matrix A? What would be a wonderful property for A to have that will make solving this really easy? So if A is the identity matrix, we could solve it, good. So what are the matrices? So identity would be a great example. What's the largest class we can think of that would contain the identity matrix where this would be easy to solve? Invertible. So if A is invertible, then it's just X equals A inverse B. Unfortunately, most of the time, A is not going to be an invertible matrix. If you have A as an invertible matrix, how many solutions will you have? Just one. So if you're trying to optimize and find the best X, and there's only one solution, the optimization problem is not that challenging. That's your only choice. So the reason linear programming is interesting, the reason operations research is interesting, is that you frequently have multiple feasible solutions, and then you can decide of all the different feasible solutions, which is the one that maximizes or minimizes the object you care about. And since different people have different preferences, you will have different people choosing different weight functions, different things to optimize. Okay, any questions on what it means to view AX equals B? That another way to view this is when we look at AX equals B, we're really looking at linear combinations of the column vectors of A. And so the only chance we have of solving AX equals B is if B happens to live in the column space. So you should have seen in linear algebra the 4 different spaces. Does anybody remember the spaces? There's the column space, row space, null space. I think there's the left null space and the right null space. The null space is the vectors that are killed by the matrix. And those are very important to study as well. Okay. So the next thing is what's called a basic feasible solution. So, again, whenever you see text like this, almost surely it's coming from the textbook. If not, I try to remember to post where it's coming from. So this is straight from the book. Given a canonical linear programming problem, so what pieces of input do we have? We have our matrix A, we have the components X that we're trying to find, we have B, we have C. We say X is a basic feasible solution if X is greater than or equal to 0. Okay, well, that's part of our canonical programming problem. AX equals B, well, that's part of our canonical programming problem. So far, a basic feasible solution, the first 2 conditions mean it's a feasible solution. Names should be good, right? A basic feasible solution, if it's not a feasible solution, the name sucks. What is 1 over cosine? What is 1 over sine? I hate this. Sorry, 1 over sine is cosecant and 1 over cosine is secant. I hate this. If it was me, I would put 1 over cosine with cosine. But it turns out that there actually is a reason for this nomenclature in terms of what is the angle, what is the co-angle. And because of that, the names actually do make sense if you look it up. But when you first hear it, it's annoying that cosine is not related to cosecant. It's related to secant. You always want to think about the names that you're doing. And so when you hear a name basic feasible solution, if it's not a feasible solution, it's a horrible name. The last one is the meat. If we have non-zero entries xj1 through xjk of X, then the corresponding columns are linearly independent. So that is the new condition that moves us from a feasible solution to a basic feasible solution. If you look at the subset of non-zero entries of X, they're associated to columns. And this comes back to when we looked at a page ago, when we looked at AX, when we multiply things out, what this is saying is whichever entries of X are non-zero, the corresponding columns are linearly independent. And in a shocker, an optimal solution and a basic optimal is very similar. Okay? So as soon as you see basic feasible, you should be thinking, why would we care about basic feasible and basic optimal solutions? Well, clearly, these are subsets of feasible and optimal solutions. The idea is, for many problems, if there are only certain things you care about, you don't care about other things, as long as two objects are identical in the properties you care about, it doesn't matter what they are otherwise. So has everybody here done clock arithmetic? You know, let's round down and say it's 9 o'clock now. What time will it be in 6 hours? 3. So everybody, we're in a 300 level class at Williams agrees that 9 plus 6 is 3. Because on a clock with 12 hours, it is. On a clock with 12 hours, 15 and 3 are indistinguishable. 3 is just an easier representative for us. But there are places where they actually do 1,500 hours. But for a lot of purposes, yeah, just say 3 as the representative. The purpose of this is that rather than looking at all possible solutions, it turns out that it is much easier to look at just the basic feasible solutions than the feasible solutions. And it's easier to look at the basic optimal solutions than the optimal solutions. And we're going to prove the theorems you hope would exist, that if there's a feasible solution, then there's a basic feasible solution. If there's an optimal solution, then there's a basic optimal solution. So what that means is if you're trying to solve the problem, you can restrict yourself to the space of basic feasible and basic optimal without losing a solution. And when I say without losing a solution, I don't mean a particular solution, I mean whether or not the problem has a solution. And again, if we do not discuss it, we do not care about it. If I am trying to find the optimal solution, and this is my objective function, and you give me 2 different choices of x that have the same value of the objective function, I'm indifferent between the 2 of them. You can't say, well, but that diet doesn't taste as good. Well, tough shit. Actually, might actually be, depending on what the diet is. You did not tell me that you cared about taste. You told me this is what you cared about, and I found something that was just as good as yours. If you want to include other things, then you have to change the objective function. And so the whole point is that it is much easier to search the space of basic feasible solutions than the space of the entire feasible solutions. And by searching just the basic feasible solutions, if we can't find a solution there, it turns out there's no feasible solution. And if there is a feasible solution, there's always a basic feasible. Same thing for optimal. So it's a much easier place to search. This is a really nice theme that for a lot of things, we only have to look at a subset to find a representative that has all the properties we care about. So if you go back to the original diet problem, we had something like this. Let's say this was the first constraint, and then this was the second constraint. And so the feasible solution was this region in here. And what we then had is we then had cost lines. And so this would be increasing cost. And the other direction would be decreasing cost. And so we would just flow along a line. And we first said, well, we can't have the cheapest diet at an interior point. Because if we're at an interior point, we can always choose a line that's parallel, that's further inward. So from that, we immediately know that the cheapest diet has to be on the boundary. And then we basically said we can somehow move to one of the points of intersection. What is the only time when we might not be able to move to a point of intersection?
If the cost line is parallel to one of the...
Good. If the cost line is parallel to one of the constraint lines, then you would actually have an entire region where they would all be the same cost. But in that case, the point of intersection would also still be a point of lowest cost. So we're not saying that these are the only points that have the lowest cost. What we're saying here is it's enough to check just these points. Now, if you look at the diet problem, in 2 dimensions, there are initially infinitely many feasible points to choose, to consider, and all of a sudden we're down to just checking 3 points. Checking 3 points isn't bad. In principle, that's what we're trying to do. That's the general theme. Most of you are never going to be solving linear programming problems professionally. That's fine. I've only done that for a very small period of my life. But what you will have is you will have problems to solve. And this idea of saying it's enough to look at a subset of the space where the action is happening and say, hey, as long as I find a good solution here, that's all that matters. And so the diet problem here is a wonderful example of what we're trying to do. We don't have to consider all possible solutions. We only have to consider 3 candidates. Okay. Any questions so far? Okay. So the next one is just basically, why are basic feasible solutions so good to study? Essentially, what it's telling us is that we can prune our matrix. If you think about what's going on, if a component of X is 0, then that entire column of A that corresponds to that component doesn't play a role in what we're doing at that moment. And so this allows us to reduce the size of the matrix. Now, what this means is, depending on which components are non-zero, we will have different reductions of the matrix. So if just the first 3 components of X are non-zero, I would get the first 3 columns. If just the last 3, I would get the last 3. If it's the first, third, fifth, first, third, fifth. So you might actually have a string of different pruned matrices A as you're going through the problem. And the hope is maybe we can prune to having A be a square matrix. If A is a square invertible matrix, can we solve AX equals B? Yeah, this is what we just talked about earlier today. We talked about the identity, and then we said we can extend from the identity to an invertible matrix. And so the idea is, if we have our columns of A are linearly independent, then maybe the matrix A will be invertible. Well, let's think about it. If I tell you that the X's come from a basic feasible solution, so the columns are linearly independent, does that mean the matrix A has to be invertible? So if I tell you that we'll look at the pruned matrix. So let's say, x1, x2, x3 do not equal 0, rest are 0. And we'll let your A1, 2, 3 be the matrix A1, A2, A3. Is this always invertible? The columns are linearly independent. Is that enough to force A to be invertible? Why not? Yeah, we don't know a matrix is square. Need square. So this might be, let's say we have R rows and 3 columns. So maybe this is an R by 3 matrix. What would A transpose be? What is the dimension of A transpose? 3 by R. So A transpose is 3 by R. So do I want to do A transpose, or do I want to do A transpose A? You've got a 50-50 chance if you guess randomly. What would be the size of A transpose A? What would be the size of A transpose? So A transpose A is 3 by 3 and is what? Square, and is invertible. So that sounds like a theorem from linear algebra. That if I take 3 linearly independent columns, as long as R is at least 3, right? If R is 1, well, if R is 1, they can't be linearly independent. R has to be at least 3, because we're assuming that the columns are independent. So if I take 3 independent columns and I form A transpose A, that's going to be invertible. So the idea is if we have, let's say A 1, 2, 3, X equals B, and I'll call it X 1, 2, 3 because we're pruning it a little bit. Then I would get A 1, 2, 3 transpose A 1, 2, 3, X 1, 2, 3 equals A 1, 2, 3 transpose B, and now we can invert. So it turns out if I have a matrix A and I trim it and I reduce it so that its columns are linearly independent, I can now solve. How many solutions will I get when I solve? 1. So this is extremely important. So not only do I get a solution, but there's only one solution. Yes?
To finish this off, you just do A transpose A, and then take the inverse of that?
No, not A transpose A, A1, 2, 3 transpose A1, 2, 3. Yeah. Yes. Yep. You would take the inverse of that and multiply it out, and then you would get, here is your vector. So what this is telling you is if I tell you which columns of A are linearly independent, and I choose a subset of them, how many basic feasible solutions can there be for a set of linearly independent columns? Almost. At most 1. And then you would have to show, will this always work?
What cases would it not?
If B is not, so the question is, what would happen if B is not in the column space? I would have to have an incredibly degenerate problem. Imagine every column of A is the same, and I choose B not to be there. I would have to have, there would just be no solution. There would just be no solution. And so, so the question is here, it looks like, it looks like this always works. I should be able to invert this matrix, but we still need B to be in the column space of A 1, 2, 3. And so, the question is, where are we using the fact that B has to be in the column space of this pruned matrix? I mean, the issue has to be if we have enough rows in the matrix, if we have enough columns, then this will always work. So the question is, what if I consider an incredibly degenerate situation where every column is the same?
Would it work? Or are we given that B is like an R by 1?
So B is an R by 1 vector. And so when we're doing this, if a lot of times we assume that B is in the column space of A. If your matrix A has real entries, this is a very weak assumption. You have to really work on things in the real world for things to be so catastrophically, reinforcing each other, not to have a solution like this. So we'll circle back to this right now. Right now, we don't actually need to know if it's 0 or 1. All we need to know is there's at most one solution.
Would it be able to be a 3 by 1?
Right. So I mean, again, my only concern is what if I take what if I take A to be 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and I take B to be 1, 2, 3. There'll be no way to solve that. And so in a situation like that, okay, so in a situation like that, if A is 1, 0, 0, this would be a 1 by 1 matrix. I'm sorry, this would be a 3, this would be a, it would have 3 rows, 1 column. It would be a 3 by 1 matrix. And then when I tried to solve things, A transpose A would be a 1 by 1 matrix. It would just be a number, it would be too small. And so what we need is we need the number of independent columns to essentially be the same as the size of B. It is a hyper-technical point to worry about. It's not going to happen in the real world when you have your real valued numbers. But the idea is that we can reduce the problem to a smaller, simpler problem. If I only look at the columns that are linearly independent, then I can restrict my action to just that. All right. So let's do things a little bit more carefully now. So this is the huge theorem. So if you have a canonical linear programming problem, if a feasible solution exists, then a basic feasible solution exists. So this tells us that we only have to look at basic feasible solutions. And the idea is something called proof by infinite descent. Of curiosity, how many have ever seen proof by descent? Where have you seen it? There's a more general one that you might have seen in number theory. Proving that square root of 2 is irrational. Or some problems attacking Fermat's last theorem. These are great examples of infinite descent. So we'll get into that if time permits at the end. Let's go through and show that if a feasible solution exists, then a basic feasible solution exists. So assume, oops, let's shift. So assume AX equals B, X is feasible, but not basic feasible. Okay. So that means the components of X are non-zero, but the columns, the corresponding columns are not necessarily linearly independent. Okay. Without loss of generality, we might as well say, consider all possible X's. Choose one of them that has the fewest non-zero components. Well, what are the possible values for the number of non-zero components? 1, 2, 3, 4, all the way up to however many components of X we have. There's only finitely many possibilities for the number of non-zero components. It could be the case that maybe the smallest number of non-zero components is 7. And then all we're saying is choose any solution, any feasible solution with 7 non-zero entries. I don't care which one, just choose one of them. So we somehow need to be able to make a choice. We are far enough in mathematics that we're not going to worry about the foundations of set theory. We're going to say we have a space, we choose one element somehow from that space. Just there's an element, we're going to work with it. So without loss of generality, assume no feasible solution has fewer non-zero entries. Without loss of generality, say x1 ... xk do not equal 0, xk plus 1, and on are 0. So again, without loss of generality, always relabel, just put whatever you want in the beginning. How many of you love indices on indices? Exactly, right? Let's get rid of indices on indices and just move everything to the beginning. So we know x1a1 plus ... plus xk ak equals 0, but a1 to ak are not linearly independent. Why are they not linearly independent? Yeah, because we're assuming X is not basic. So by definition of what it means to be basic, If you're basic, then the corresponding columns have to be linearly independent. Since you're not basic, they're not linearly independent. Thus, there exists alpha 1 dot 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 alpha k such that alpha 1 a1 plus dot 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 alpha k ak equals 0. And it's 0 the vector. Right. Oh, wait a minute. It's not equals 0 over here. It's equals the vector b. Okay, so we know we can choose the alphas so that this linear combination equals 0. Okay. What we want to do is we want to get rid of one of the components x. So if we look at a, and let's call this vector alpha 1 dot dot alpha k, let's call that the vector alpha. So if we look at a x minus lambda alpha, what will that equal? It will still equal b. Does everybody see that this still equals b? Because ax equals b and a of alpha equals 0. If lambda equals 0, we get back a old solution. So we're considering, x lambda is x minus lambda alpha. When lambda equals 0, we get x. What happens as we increase or decrease lambda? What happens to the components of x minus lambda alpha? So we start off, do we agree that when we have x, every component is positive? As we increase or decrease lambda, what's eventually going to happen? And all components are positive. Let's say for simplicity, all the components of alpha are positive as well. Just let's make things easy in the beginning. So all the components of alpha are positive. What happens as I increase lambda? What happens to the components of x lambda? What happens to x minus lambda alpha? If all the components of x are positive and all the components of alpha are positive, as lambda increases, what must happen at some point? Before it becomes negative, something must hit 0. One of the components, it might be several components hitting 0 simultaneously, but as I increase lambda, at least one component becomes 0 and everything else is still positive. If some of the components of alpha are negative, then I might need to take alpha to be negative. Okay? But there has to be a direction to move alpha, to move lambda, where at some point, one of the components here has to become 0. And when it becomes 0, maybe another component became 0 with it, but all the components that are not 0 have to stay positive. This is essentially the intermediate value theorem from calculus. You can't go from positive to negative without crossing through 0. So if you look at each component, look at it component by component. For each component, there is a choice of lambda that makes it 0. Maybe for the first component, it's lambda equals 5. For the second component, maybe it's lambda equals -2. For the third component, it's lambda equals 5. The next one, maybe it's lambda equals pi. So for each component, there's a value of lambda that first makes that difference equal to 0. And then take the smallest lambda in absolute value among these, and then use that lambda. And for that lambda, you have one fewer component. So special lambda where at least one component of x lambda is 0, rest positive, and this is a contradiction. So what does this contradict? The view is non-zero. So this is an absolutely wonderful proof. You assume that there's a vector with a certain property, and then you show that you can find, with a minimal property, and then you show you can find something better. Well, that can't happen. We assumed we had the minimal one. So another way of looking at this is if you have a feasible solution and all of the columns are not linearly independent, this tells you how to move to another feasible solution. So this is similar to going back to the gradient and Lagrange multipliers in multivariable calculus. Not only does the fact that if my grad f is not parallel to grad g, do I know I'm not at a max or min, but it tells me which direction to move. This is giving you a suggestion. Hey, try the following. It will reduce the number of independent components. Could this process go on infinitely often? No. And so that is the next theorem. There are only finitely many basic feasible solutions. Is assume x is basic feasible. And so we're solving ax equals b. Say b has n components. So x has 1, 2, ... n components. For a given number of components, there's at most one solution. At most, one basic feasible solution for each set of linearly independent columns. So only finitely many. And this was coming from the, say, a prime x equals b. We then went to a prime transpose ax equals b, to then x equals a prime transpose a inverse. Oh, I need an a prime here. A prime b. So once I tell you which columns I have, there's at most one solution. How many ways can I choose columns from A? Well, if I'm choosing finitely many columns from a set of finitely many columns, is it clear that this is finite? Yeah. You can give me an upper bound for how many ways there are. You can actually compute just how finite this is. I don't care. All I need to know is that there's a finite number. Now, from a practical point of view, I might actually care just how finite is the number, because that might give me a sense of how long it's going to take to run. But from a practical point of view, all I need to know is there's only finitely many subsets of columns that I can take. Each subset of linearly independent columns has at most one basic feasible solution. So there's only finitely many basic feasible solutions. Okay. There are similar results for optimal solutions. I'm not going to bother going through the proof. The proof is very similar. It's in the book. If you have any questions, always happy to chat. I want to just end with another example. This is considered a rite of passage, is you should have seen at some point in your life with the square root of 2. Here's the proof by descent. So proof, assume not, say the square root of 2 equals a over b with b smallest possible. So we will assume that there is no fraction with smaller b. Well, it's clear that if there's multiple ways of writing the square root of 2 as a ratio of integers, there's going to clearly be one with the smallest denominator. So we get, if we square 2 equals a squared over b squared, so 2b squared equals a squared. If a is odd, a squared is odd. So, 2k plus 1 squared is 4k squared plus 4k plus 1. So the only way 2 can divide a squared implies 2 divides a. Because if a was odd, 2 cannot divide a squared. So we can write a as 2 times m. So we get 2b squared equals 4m squared. So b squared equals 2m squared. Argue similarly, and we get what must be true about b. Yeah, so once we had 2b squared equals a squared, we saw that 2 had to divide a. Now we have b squared equals 2m squared, so 2 divides b squared, 2 has to divide b. So we get 2 divides b, so say b equals 2n. So the square root of 2 is going to be a over b. A was 2m, b was 2n, which is m over n, and n is less than b, contradiction. So this is the method of descent. We assumed that we had a minimal representative, and we found something that was even smaller. So our assumption that there was a representative is false. So again, proof by descent is absolutely wonderful. How many people had never seen this argument before the curiosity? Okay, so you are now allowed to graduate from Williams with a math degree. This is something you just have to have seen at least once. The following, so everybody has to give a colloquium to graduate. You are not supposed to be talking during a colloquium. Years ago, someone was giving 6 different proofs of the irrationality of square root of 2, and Professor Morgan whispered to me, there's a beautiful geometric one. If anyone's interested, you can click on the links. You can actually prove that the number square root of 2 is irrational by drawing squares. And he remarked to me, it's a shame that it only works for squares. And of course, my attention was completely devoted to the speaker. Coincidentally, as soon as the talk was over, I passed a napkin to Professor Morgan. I've been having a cookie, because you could actually eat during talks back then, with a proof of the irrationality of the square root of 3 by generalizing the argument. And again, it's a little bit different than the descent argument. It's a little bit different, but it's still a descent argument. It's not algebraic, it's more geometric. And you can show that if you had a minimal solution, you can find an even smaller one. You can prove the square root of 6 is irrational. You can prove the square root of 5 is irrational. I have not been able to get the square root of 7 or the cube root of 2. I will give an A+. I don't care that this class doesn't really involve these problems. If someone can get the square root of 7 is irrational or the cube root of 2, you can have an A+ in either this class or in any future class you take from me. And I do realize that this is being recorded now. I would absolutely love to see that work. It is hard. I have had students spend a year in frustration on this problem. And again, if you're interested, happy to talk more. One of the things I want to do with this class is just show you connections of math. All right, so this is a good place to stop.